In this module, we are going to observe energy consumption with power capping. We are going to manipulate power caps and see how power capping influences various metrics related to energy consumption of a program. This exercise is intended to be performed using the supply Docker image. First, we have to check how much power is consumed when the program is executed without a power cap to get a reference value. Today, we are using the MG Class C benchmark. Remember that I'm running the benchmarks without recording my screen to get more accurate results. We can see that the program consumed about 1600 joules of energy during about 19 seconds. When we divide these two values, we will get the average power consumption in watts. In this case, it is about 84 watts. Now, it is important to select which constraint should be used. Let's see what's the difference. Constraint 0 is a long-term constraint applied over a long time period, whereas constraint 1 is short-term constraint applied over a short time period. These constraints may be set independently, but we are focusing on constraint 1, which is the short-term constraint, as the benchmark does not take long to execute. We can now set the power cap to 80 watts. Notice that we are setting the value in microwatts, so we need to append 6 zeros to the value in watts. Now, let's execute the benchmark again. After it finishes, remember to write down the energy and time for each power cap. Here, you can see that the program already consumed a little less energy, but took a little longer to execute. Now we can set the power cap a little lower, let's say 70 watts. We've got yet another pair of values, so let's continue. I set the constraint to 60 watts. After going through multiple power caps, 60, 50, 40, 30, 20 and 10 watts, I've gathered a table with 3 columns: the power cap value in watts, the energy in joules, and the time in seconds. We can now plot this data. The first plot shows how the energy changes depending on the power cap. We can clearly see that the lower the power cap, the less energy is being consumed. The second plot shows the time the benchmark took to execute depending on the power cap. The time does not change much and stays within the range of 18.9 to 19.6 seconds. Finally, the third plot shows the EDP metric. According to this metric, the optimal power cap is somewhere between 40 and 10 watts. Please keep in mind that these plots and behaviors are unique and might change depending on the program, the hardware, or even the software.